Hello everyone, welcome to this video. In this video, we'll be looking at the proof of the theorem that we discussed in the previous video. So here the statement of the theorem, let me remind you again. It tells us that about the number of elements of each order which are present in a finite cyclic group, right? So if D is some positive divisor of the number n, right? Where what is n? N is the order of the cyclic group, right? Then the number of elements which would have this order D would be calculated by calculating phi of D. Where what is this phi of D? It is known as the Euler phi function, and it results in calculating the number of elements such that say x is that element such that the GCD of x with D is equal to 1. So that means it will give you all those elements such that the GCD of those numbers with D is equal to 1, or they are relatively prime to D, right? So it will provide us with the count of all those numbers. So let's see the proof how we may reach at this phi of D here, right? So we assume that D is some positive divisor of n, right? And we have a cyclic group which would have order n. Then we will prove that the number of elements which is having order D is precisely given by this phi of D, right? So according to the fundamental theorem of cyclic groups, we already know that the group has exactly one subgroup which is of order D. So we can call this by the subgroup which is generated by A, right? So by the fundamental theorem of cyclic groups, the group has exactly one subgroup of order D. We are calling it by the group which is generated by A. Then every element of D also generates this subgroup, right? Why? Because we have exactly one subgroup of order D, right? So every element of D also generates the subgroup this which is generated by A. So every element which would have order D, right? Remember this thing, every element which has order D also generates this subgroup, and moreover, according to the following result, this we have studied that whenever the order of element A is n, then the subgroup which is generated by A is equal to the subgroup which is generated by A raised to power j, such that j is such that the GCD of n with j is equal to 1. So that means this power should be relatively prime to the order of the given element, and moreover these two orders, they are equal to each other if the GCD of n with j is equal to 1, right? So using the result here, we would say A raised to power k would generate the subgroup generated by A if and only if the GCD of this power k with the order of this one, which is D, right, is 1. So that means this power k is relatively prime to the order of this element A, which is D. So GCD of k with D is equal to 1. So according to the definition of phi of D, what does it give us? It would give us all those numbers such that the GCD of those numbers with D is equal to 1. And this is what we are saying, the GCD of all those numbers k which are relatively prime to D, right, is equal to 1, and we count those numbers by the function Euler phi function, right? So this function count how many such elements are there. So this is what we wanted to prove here in this theorem. So we wanted to prove that the number of elements which would have order D is exactly phi of D, right? So moreover, you could note here that for a finite cyclic group, so until now we were only talking about finite cyclic groups. So whenever we have a finite cyclic group where the order of the group is n, then the number of elements having order D for any divisor D of n, so you have n as the order of the group, and order of which group? Order of finite cyclic group, right? So when you have n as the order of finite cyclic group and D is some divisor of n, right? So in that case the number of elements of order d would depend only on d. How this is so? In Z8 and in Z640 and in Z80,000, right, you have 8, d is equal to 8 as divisor of n, and which is the order of the group, right? So that means 8 is the divisor, so that means all the subgroups which are of order 8 would have how many elements? They would have exactly 4 elements. Why? Because phi of 8, the Euler phi function of the number 8 is calculated, and according to our previous examples here, right, for 8 we have the value of phi of 8 as equal to 4. So therefore in this case this is equal to 4. So that means in all the 3 groups here, the subgroups which are generated by 8, not 8, the subgroups which in which the order of element is d, which is a divisor of this 8, 640 and 80,000, in that case those subgroup would have exactly 8 elements within, exactly 4 elements within it, right, and all these 4 elements would have order 8. So I hope you understood this theorem well. That is it for this video. Thank you for watching.